So, hey guys, welcome. Thank you, Edward, for inviting me to speak with ACM today. My name is Eric, and today I'll be talking about an algorithm called Proximal Policy Optimization, or PPO for short. Before we begin, I just want to know how much experience does everyone have with reinforcement learning, deep reinforcement learning, or even deep learning for that matter? You want to put in the chat there? Okay. 150B. I think I've seen you before, Jason, in the Slack channels. I tutored 150B last quarter. I've started reading paper on multi-agent deep reinforcement learning only very recently. So you do have experience with single agent then? Because interesting. Typically you want to build off from single agent into multi-agent. Not much experience with RL specifically, none. Okay, so I'm going to tweak my presentation a little bit then, because it is a little bit more advanced or geared for an advanced audience, but that should not be an issue because PPO is rather straightforward. So let's get down straight to it. So before we talk about PPO, I just want to talk a little bit about myself. So my name's Eric. I'm a third-year CS undergrad, and I currently do research under Professor Sikun Gao. And my particular focus is on safety in intersection negotiations with autonomous cars. And yeah, that's kind of what I do right now. I tutored CSE 150B, Introduction to Artificial Intelligence last quarter, and I tutor a few other classes with Gary Gillespie. But let's dive straight into it. So I'm here to talk about PPO, or Proximal Policy Optimization for short. And our first question should be, what exactly is PPO? Well, I guess if you really want to, you can hop on the actual source here. And here's the quote unquote paper that OpenAI published about a few years ago, I think 2016-ish. And so, if you've read it, it might have been a little bit confusing, especially if you don't have too much experience with reinforcement learning. Certainly the first time I read it, it wasn't very intuitive at all. But that's why we're here, is to get an intuitive sense of what's going on and why this algorithm is important, pretty much. I'll talk a little bit about the history of PPO right now, actually, or rather, once I define it a little bit better. So PPO is what we call an enhanced policy gradient learning algorithm, and this is in the field of deep reinforcement learning. So I know a lot of you guys don't have too much experience with RL in particular, so let me just break this down. Reinforcement learning is one of those subfields of AI as a whole. Just like machine learning is, recommender systems, you have deep learning, supervised learning, unsupervised learning. Reinforcement learning is just one of those subfields. And what makes it different and what makes reinforcement learning unique is that it's like having a robot or an agent learn to play in a video game. So you're putting this robot inside its own world, inside a simulation, and it's got to figure out by itself how to play in the simulation, how to abide by the rules, and basically maximize some reward that we feed it. Which is different from supervised learning, right? It's just a completely different idea. Where supervised learning, we have a data set, right? We have features or our data, and then we have the labels associated with them. And the whole point of our network is to learn the patterns given the data, right? We're trying to basically associate the what we're given to what the answer is and see if there's any patterns in between there so that we could predict future data. Whereas reinforcement learning is, no, the robot kind of does something similar, except it's just playing in a simulation, which in my opinion seems a lot more AI-like. Now, what puts deep into this is the fact that we use neural networks in all this. So neural networks, Whenever you hear the word deep in pretty much anything AI related, it just means we're throwing in some neural networks in there and doing some back propagation to train those neural networks. And that relates a lot to what we call policy gradient, which essentially builds on this deep part. So we use neural networks and we train these neural networks to learn something useful for our little agents to do something useful in these simulations. Okay, now I know that was a lot to take in, but we'll go on and reinforce this idea, no pun intended. Now there's something special about PPO. Okay, so again, proximal policy optimization is PPO for short, which is our learning algorithm, and that it builds on our classical policy gradient algorithms. So we have something called reinforce, which is a very classical policy gradient. We can use neural networks in this as well, though it's not mandatory. But PPO builds on this by increasing the stability while decreasing the complexity of our implementation. And this also makes sure that we have at least as good performance as when we started off. So that's the important part, is we get easier learning, right? It learns a little bit more stably. And we'll see exactly how it does this. In the paper, there's basically two main contributions that it presents. Number one is called the clipped surrogate objective function. And the second one is basically having multiple epochs per policy iteration. Now, the first one, clipped surrogate objective, is basically just its loss function, quote unquote. If you've had any sort of machine learning experience, a loss function just tells you how good you did during that training iteration and whether, how much you need to be changing by. And so an objective function or performance function in reinforcement learning is basically the complete opposite of a loss function. It's actually the negative loss function, which states that we need to be maximizing whatever function this is, right? So with using a clipped surrogate objective, we'll see that it actually controls how much we're changing our network, all the little weights and biases in our network. We're controlling how much we're changing those by each time so that we're not overshooting or undershooting in our error surface. And the second one is the multiple epochs per iteration, which basically states that we're going to be changing our weights many times per batch or per iteration, per however many simulations we gather and we're ready to make updates to our network. And by doing this, it increases our sample efficiency. As you might imagine, you grab the same amount of data, but you're getting more out of it. Now, looking at the first thing, it's a clipped surrogate function. Like with any sort of deep learning thing, we always have an update rule. And in this case, this is the definition of the update rule, where theta is the parameters of our network, all the little weights and biases, is represented by this variable called theta. And theta, excuse me, at the kth iteration plus one, so the k plus 1th iteration, which in other words is just the next iteration or the next version of our theta, is equal to the argmax of, or the argmax of theta of the expected value of our L function, which is our performance function. And in other words, we're trying to find a set of theta that maximizes our expected performance. That's the way to think of it. And here is exactly how our performance function is defined. Our performance function, given a state, an action, the old set of parameters, theta, and a new set of parameters, theta, is equal to the minimum of these two things right here. And these two things are what we call our surrogates. A surrogate in English, as we might think of it, is like a substitute, right? It's like something we put in place of something else. And that's something related to this, where, depending on which one is smaller, that one is going to be the surrogate of our entire performance function. Okay, now to break this down right here, okay, I know it's a lot of weird symbols and all that, but the idea is we have two parts in our function. We have a ratio right here, and we have an advantage function. The ratio tells us how much more or less probable our actions are in the next time step or the current time step. And the way to read this is to say, okay, well, we have pi, which traditionally is the symbol for our policy. Okay. Now pi, with the set of parameters theta of an action given a state, this entire thing right here, and I think I'm lagging a little bit, this entire thing right here is going to yield the probability that we take this action given this state using these set of parameters. Okay, so again, this thing right here is the probability that we pick action A given S under this policy, under this set of parameters theta. And this whole thing is divided by something very similar looking, except we have this extra K down here. And again, theta sub K just means the old parameters. So we have the new parameters and we have the old parameters. Now, in the new set of parameters, if this value is larger than the bottom one, we can say that the action, the probability we take this action given the state is going up, right? If this whole thing is greater than 1. And if this whole thing's less than 1, it means this top term is smaller than this bottom term, which means that the action given the state has a less likely chance to be selected than when it started off our iteration. Okay. And so this will pretty much either be greater than 1 or less than 1, somewhere around there, but it won't be too big. But when it does become too big or too small, that's when PPO kicks in. Okay. But I'll talk about that in just a moment. Now, advantage, you don't need to know too much about this. Just think of this as how good our current state is given an action. So how good is this action in this state? And it just returns some sort of value. And again, don't need to worry too much about this. In fact, this term right here is exactly the same as this term, which means that the real variable here is this left term when we're comparing these two surrogates. Okay, and what makes this right side particularly interesting is this clip function right here. Okay, so you see that we have this ratio again on this side, but what makes it special is we're clipping it between these two bounds. So 1 minus epsilon and 1 plus epsilon. And what it's trying to say is basically, I want this ratio, I'll keep this ratio as it is, but if it ever goes below this lower bound or above this upper bound, we're going to set it to either one of those bounds. Okay. Now say epsilon is 0.2, which I think is the standard. Then this lower bound is going to be 0.8. And this upper bound is going to be 1.2. All right. Now let's say our ratio becomes 1.1. 1.1 is between 0.8 and 1.2. So we'd actually just keep this. We wouldn't do anything with it, right? But the moment the point, this ratio becomes greater than 0.2 or 1.2, or becomes less than 0.8, then suddenly we have to start referring to these guys right here. Right? So if this becomes 0.7, right, then it's lower than the lower bound, which is 0.8. And so this entire thing is just going to return 0.8 because we're trying to keep this value between these two bounds. And the moment this value right here, the ratio, steps out of bounds, we just set our value equal to whatever bound it overstepped. Okay, so that's the basic idea. We have this clip function that's going to limit our ratio between these two values. And then we take the minimum from there. Now, I could go a little bit more into the intuition of this, but I think the main takeaway is that this ratio is like a scalar, which tells us how much we need to be moving our weights, right? So if you think about our error surface in deep learning, right, it's 3D error surface, we're always trying to move towards a point of, a minima, which is just classical deep learning. In reinforcement learning, you're actually doing the opposite. You're trying to reach a maxima, right? You're trying to reach a local maxima. Except the issue is you never know how much you need to step by. Typically, you use gradients to know where to step, and gradients will tell you, what direction to go by, but you never know how much to go by. And so that's what these sort of algorithms in deep reinforcement learning are trying to solve. They're trying to tell you where to go as well as how far to go. Let's see, David says, so there's a modification to the function optimization using the neural network rather than modification to the policy optimization algorithm itself. Yeah, so I mean, you're modifying the loss function, and the loss function, this update rule is just part of the algorithm. The algorithm itself is, again, an enhanced policy gradient algorithm. And policy gradient is all about, neural networks. So the training part is very similar across all these different algorithms. The main differences are just how they calculate that loss function and, how they're getting the data and what they're doing to the data and whatnot. If we set L to the clip function here, would that achieve the same result? I don't believe so, no. And the reason why is because of this advantage function here. Now you could, if this advantage was always positive, then I think you could just get rid of the left-hand side and just say, okay, just stick with this. But sometimes the advantage can be negative. And so I don't want to get too much into like, okay, well, when it's positive, what happens? When it's negative, what happens? But basically, you need this min because of the fact that advantage can be both positive and negative. And so that'll basically control, when it becomes negative, everything becomes inverted. So the min just regulates that essentially. There are times when the ratio is small though. Yeah, so that's why we have this 1 minus epsilon to make sure that, to make sure that it is gonna step a little bit at least. But if advantage is positive again and you get a really small ratio, it means that you're approaching your maxima. And so you shouldn't even be moving that much to begin with. So that's correct. So that's sort of the whole idea here. And again, this is just an update rule, which is a big part of PPO again, right? This is one of the two contributions that PPO presents here. And the whole idea is just making sure that we're not stepping in either direction too far. Now, the second contribution it adds is multiple epochs per iteration. Okay, so the way reinforcement or deep reinforcement learning works in PPO is you gather a bunch of data first. So you run a bunch of simulations and you gather a bunch of data. And once you gather a set amount of data, you then perform an iteration, which an iteration just means you're updating the weights of your network. Okay. And so the idea is typically in deep learning, you only perform one epoch per iteration, right? Or when you perform an epoch over your data, you run through the data and you update your network once, essentially. There's one update. And in this case, we're going to be updating the network multiple times within one iteration. So we collect a batch of data and then we update the network multiple times with that single batch of data. Okay. And what this allows for is more sample efficiency, right? If we're updating our network more than once per iteration, it allows us to get more out of our data and to reduce the training time. Now, obviously, there's going to be some dangers with this. The biggest one being that you could overstep again, right? The whole point of PPO is to not overstep. And by increasing the amount of epochs, you're increasing that possibility. But PPO is designed in a way where it's going to regulate that overstep. And also, it is a hyperparameter, so you probably wouldn't want to set it too high to begin with. I think typically the default is like 80, though I don't know if that's a great idea in a lot of cases. Again, it's just a hyperparameter, so you can set it to really whatever you want. Now you can see how they kind of use that in the pseudocode. Okay, quick question. Just to clarify, this is for direct policy gradient algorithms or methods. Is there anything similar for value-based algorithms? Or is the issue that PPO addresses not particularly an issue with value-based methods? So PPO The funny part is the way you implement PPO does include value-based methods, or like some to an extent. There's something called an actor-critic framework, which states that there's going to be two networks when you're training. One is going to be your actor, which tells the agent what to do, and one of them is going to be the critic, which tells you how good your state is. You know, it tells you the value, an estimate of the value of your state. And using those two, you can basically update both networks. And it's actually incorporated in the pseudocode here. We'll take a look at that. But PPO mainly focuses on updating the policy directly. We're not like, it's not Q learning where we're saying, okay, well, this state with this action has this value. So we just pick the maximum, the argmax of those. PPO is just going to say, okay, let me see how I do. Oh, I didn't do too well. Let me just update the policy directly. So the next time I do something, the policy's updated and we're not looking at any table to say, okay, let's pick the one with the highest value. We can go a little bit more into that during the discussion. Now we can look at the pseudocode here real quick. And it's only 8 steps, but it can get a little bit confusing, especially when you look at it for the first time. It's called PPO Clip. That was the original name by OpenAI. And the idea is we have this for loop where K is the iterations, right? So first of all, we initialize our policy parameters as well as the value parameters. So here's where the actor-critic framework comes in. We have an actor, which is the policy, and we have a critic, which is the value function. And both of them have their own separate parameters or weights and biases. And for each iteration, we're going to collect a bunch of data through simulations. Okay, so collect a bunch of data through simulations. And then we're going to compute the estimated values of each state given in action, okay, of those simulations. And then from there, we're going to compute an estimate of our advantage. And after that, we're going to update the policy using the clip surrogate function that we were looking at earlier. And this is done using stochastic gradient ascent instead of descent, because again, we're working with a performance function. So that's the negative loss. So we're trying to find local maximas. Okay, so stochastic gradient ascent, not descent, with an atom optimizer. And then after we update the policy in this iteration, we update the value function in this iteration, you know, through something like mean squared error. It really doesn't really matter. And that's through gradient descent. Okay. And you just do this forever and ever, and it should converge somewhere. Okay. Now, again, this can be a little bit confusing, especially when you're trying to implement it. So I actually wrote a series about half a year ago, a little bit more than that, teaching people how to write it from scratch with PyTorch in Python. And so I'm going to open this up real quick. Some fun facts. It was published in 2 publications. One's called Analytics Media, which is a very large Indian data science organization, and The Startup, which is actually the world's largest medium publication up to date, or the largest active one at the moment. So that's really fun. But here is my little series. I'm just going to paste this link in the chat here in case you want to follow along, or you can just look at my screen. But the idea, again, is to teach the person who's interested how to write PPO and how to implement the pseudocode that we were just looking at. Okay, so we can go, look through this, and I provide a little pipeline for how my code works. You can look more into that in your free time. I show some results, which basically says how good my code did relative to state-of-the-art PPO implementation. Which state-of-the-art includes all the little optimizations that you can do, which I actually just avoided completely. So that's why my little green graph here does not perform as well as the state-of-the-art, but no, that's all good. And then the left-hand side shows what task we're performing pretty much. So this one was, balancing the little pendulum on top here. And then this one is teaching this little quadruped or bipedal walker how to walk. And then again, here's the performance graph. We have this one, which is teaching this little lander or this little rover how to land given an initial perturbation at the very top. So it's going to fly itself safely on the ground without crashing. And again, I do relatively okay. And this one, which is supposed to try and get a little bit of, what do you call it, acceleration, momentum, excuse me, try to get a little bit of momentum in order to reach the flag. So if you just try to go forward from here, you're not going to go up the hill. But if you sort of swing yourself up, then you're going to hit the flag and get a big reward. And unfortunately, neither my thing nor the state-of-the-art actually managed to pass this one, state-of-the-art PPO implementation. And we can talk a little bit more about that in the discussion, but that was as expected. PPO does have its limitations, and that's why in deep reinforcement learning, we always have many, many different algorithms because each one has their pros and cons. And so, you know, in part 2, I started talking about how you can actually code the thing in Python. And so, you know, if you're interested, you can look through that. And yeah, really cool stuff here. Now, the next sort of thing I want to talk about is the code. So I'm just going to give a quick preview of the code here. One thing to note is that I wrote this code and this series here with the assumption that you're familiar with 3 things, okay? And it's reinforcement, classical reinforcement learning, so what you learn in CSE 150B. I assume you're okay with policy gradient algorithms, and I assume you're actually fine with the PPO theory. And if you're not, I actually provide some very, very nice links, actually handpick them, places where you can learn about these different things. Like if you're interested in policy gradient, this article right here will explain everything you need to know in a very nice manner. Speaking of which, researchers, turns out that they're not the best of explainers. They're very smart, but rather terrible when it comes to teaching. So that's kind of one of the reasons why I actually wrote this series, was because all the little guides I found online were sort of junky, and I figured there's a lot better ways to do this. So yeah, again, I'm just going to throw the little repo link here in case you're interested, and you can always look over it. So let's talk about some potential optimizations as well as some pros and cons. So we looked at vanilla PPO just now, but there are some different ways you can optimize it in code. And one of the bigger things is obviously the network you're trying to use, right? So there's many different options you can go with this. You can make your network wider, you can make it deeper, you can use a multi-layer perceptron, you can try using a recurrent neural network. This will probably mean you have to modify the way you collect your data a little bit so that it's sequential, but it'll probably work, you know, depending on the situation, it might work out better than a multi-layer perceptron. There's many different techniques you can employ, such as batch normalization, there's dropout, you know, L2 regularization, and these in particular will decrease the chances that you'll or increase your potential of generalizing to the data and to the actual problem or the solution. You don't want to be overfitting to anything. Normalization turns out to be a huge thing when it comes to optimizing any sort of reinforcement learning stuff. Particularly normalizing the advantages turns out to be extremely useful. The rewards that you distribute to the agents and the data that you give to the agent. So normalizing it will increase stability of your learning, as well as hyperparameter tuning, that's a given. And there's a lot more. So using PPO, you can get a lot of fun results. Okay, so right here, I have a quadruped which learns how to walk by itself using PPO. And we'll see 2 robots here. There's a grayed out one and a solid one. And the grayed out one is using the state-of-the-art PPO implementation. And the solid one, the solid one is the one that I have without any sort of optimization. And we'll just take a quick look here. So it turns out that this robot, you know, the grayed out one again is what state-of-the-art learns, okay? And it walks pretty well. And then the solid one is my robot, which sort of learns a little spider crawl, right? So it spreads out its legs a little bit to gain more stability, gain more balance, and it sort of hobbles forward. And it keeps pace relatively well, which is pretty interesting. So PPO is a very powerful reinforcement learning algorithm. Why I can't escape this. And it's a very powerful reinforcement learning algorithm, which is employed a lot in research. And today, hopefully you've gained some insight into one of these algorithms. So I want to open this up to discussion because I'm sure there's a lot of questions you guys might have or a lot of things that you guys just want to talk about. So you guys feel free to unmute yourselves and let's have a little chat. And also ask me if there's anything I can talk about.
Could you explain PPO? Like, what's the difference between PPO for beginners compared to like actual PPO?
Yeah, well, they're both PPO. They're both following the same implementation. It's just that there are what we call baselines online, where they implement a very robust, a very reliable implementation of PPO with a bunch of optimizations in there. So like the optimizations we just talked about with
oh, okay. So like you have different parameters and all that, right? So
with different what?
Your hyperparameters are just a lot different. And like some of these architectures are different, right?
So they're different. Architectures are different as well. They probably also normalize a bunch of crap. I don't do any of that. Yeah, the only thing I employ is actually advantage normalization. But other than that, I use a very basic MLP, and I only normalize advantages, nothing else.
I see.
Yeah, and again, my thing is coded from scratch, and it's designed to be intuitive. So it's designed for someone to look at this and make sense out of it. You'll find that a lot of the implementations online are very non-intuitive. In fact, you're going to spend days just staring at it and you won't get anything out of it because it's just, there's so many different rabbit holes and so many different layers of code that it's really hard to keep track of what you're looking at and where the actual PPO implementation is. But my code is designed for beginners so that you can look at it and you can make sense out of it.
When I'm trying to like read your GitHub, what's the difference between what's the graph code folder for? Because there's PPO in there.
So I was looking at these graphs earlier, right? So these things right here, and the graph code is basically how I generated these things. So if you want, you can also generate your own set of graphs like these by just running what I have. So I have instructions for you. If you go to graph code here, there's a set of instructions which will tell you exactly how to generate what I created here. Now note that these figures collectively took over 10 hours on a GTX 1080, so it took overnight. And so yeah, it took a little bit. So just warning you.
How big was the network then? For 10 hours?
Very standard. In fact, I think you can just find it right here. Let's see, network.py.
3 layers.
6, yeah. Very standard.
10 hours, okay.
Yeah. The updating part isn't the issue. It's the data collection. Data collection is always the longest.
Oh, really?
Because you're running simulations, right? Updating the network isn't that bad. You look at all these the data, you normalize it, or you perform some processing, and then you just update the weights. The collecting the data itself means you have to basically play the game. You have to play the game a bunch of times.
So it's the environment that's slow.
Right, exactly. That's the bottleneck.
I see.
So to clarify, the main motive, like the motivation or why PPO was kind of made is because with like a policy gradient method, if you're taking too big of like a step and you're changing your actions or the probability of taking some action out of state drastically, then you would change all the future dynamics. And so it's kind of like you would you might end up in a very completely different like reward area.
So PPO actually, yeah, so something like that. PPO does build itself off of a previous algorithm. So it's like it's a better version of something that existed. And that thing that existed is what we call trust region policy optimization, or TRPO for short. And what that is basically, number one, when you're doing updates on the error surface, right, you're moving somewhere, it not only tells you, it's a little bit different than gradients. It tells you what region around you is safe and you trust that you should go in. And then once it figures out this trust region, it then figures out a point that is optimal for you to step
within that.
Yeah, so it's like within that, it then tells you where you should go, right? And then you make your weights to kind of go in that area. Now, some cons about this is, number one, it's very difficult to implement, right? Not intuitive at all, and not very easy to understand. And I believe it was rather slow, or about the same speed. But either way, the big thing was that it was way complex. And what OpenAI ended up doing was, if it created PPO, and it found that it could achieve at least as good performance as TRPO, or about the same, but make the implementation a lot easier. A lot easier. And the way to do this is still by using gradients, which gradients will tell you what direction to step in, except you kind of control how much you're stepping by. They're not overshooting or undershooting by anything.
Yeah, and the idea is that it's not having to compute a much more difficult, like, general thing of like, oh, like, how big is this trust region? It's just saying, like, just don't.
It's a lot less computation, yeah.
Yeah. Okay.
And it achieves about the same performance.
So this is something that, like, I don't understand well at all yet. But with regards to, like, search methods, I believe, where it's like you're just exploration within various, let's say, policies, like, does this affect that as well? Or I would imagine it probably wouldn't.
Search, can you elaborate?
So I guess search would be like when you would take exploration moves where you change your policy, let's say, in a significant way, in order to just see what other potential, like, policies you could have. So something that's like a drastic change where it might be very, very difficult. So for example, in the car that has to go up the hill, you could have, you'd have a very large amount of your policies, which would involve, like, small changes to how much momentum you start with. Or you could potentially explore some very drastic policy where it's going to be like, just push it as much as you can.
So that's one of the limitations, actually, of PPO. Thanks for bringing that up. PPO builds on itself. It's what we call an on-policy algorithm. And what that means is that it updates itself as you're collecting data and as you're training. This is different from what we call an off-policy algorithm, where you're just collecting data and you're just randomly sampling from that data. And even when you're collecting data, you're just randomly sampling actions. So there's no correlation between your current policy and the data you collect. Now, obviously, an on-policy algorithm, if you're updating your policy and making it better as you're training, the data you collect should theoretically be more quality, right? Because that means you're making better decisions as you go along, and then you ultimately reach some sort of maxima, local maxima, which is as good as it gets, right? But
sorry.
No, sorry. Same.
Yeah, I guess so. The idea is, maybe I misunderstood what I read, because I read this like once and I don't remember. I can try to find it again. But the idea would be kind of with just a regular algorithm like this, you would find a local optima. But if you're trying to find kind of global optima, you would want to try kind of just certain policy updates that are going to be drastic.
There's no good way to find a global optima. Well, that's the whole thing about deep learning. In deep learning, you basically can't find the global minima or global maxima.
Yeah.
Because that would mean you have to search everywhere, and that is exponential, if not infinite. Now, the whole point of deep learning is that, typically local minimas or local maximas should be good enough, right? Now, obviously, some local minimas or maximas are better than others. So that's why we perform something called k-fold cross-validation, which states that we're going to start off with a different random set of parameters per iteration or per new training cycle. And then some of those will start off at better spots than others. And so the slope that they go down or go up is going to be better than maybe in a previous cycle. Right? So K-fold basically states that, okay, we're going to try training multiple times and we're going to pick the one that trained best out of all of them. Right?
Okay. That would make sense.
Yeah, and you can implement that here, right? It's just a matter of, how long do you want to wait, right? Typically, a local minima is good enough. And if you want to achieve state of the art, or you're trying to publish a paper, then that's when you might want to consider doing a lot of different stuff. All right, bye, Stone. But yeah, I hope that answered your question. You can't find a global maxima.
Yeah, I understand that. I thought the idea would be like in games like this where you could just try more drastic policies just to kind of get out of whatever local range you're stuck in. Because with PPO, you wouldn't be able to travel particularly far from your initial policy.
Yeah. Now, interesting part about this, by the way, I've trained this many times, and sometimes it will learn to do it.
Okay.
But most of the time, it will just reduce back down here. But there are many different techniques and many different algorithms that do counter this, right? Because this is a big issue with policy gradient in general. Is policy gradient as a whole, you're basically trying to improve your policy as you train and basically smoothly move towards the place that you want to be at. And that sometimes isn't the best way, because if you try to think of it that way, then if you get stuck anywhere, it's really hard to get out if you have to do anything drastic, right? In this case, your drastic action, you have to come here and you have to swing back and you have to swing back. And that's a really, it's not that complex if you think about it, but it actually takes a sequence of actions that's pretty coordinated in order to reach here. And so the likelihood that you do that is not very high. And even if you do that, it's likely not going to learn enough, right? As you notice in my graph, my thing is actually unstable enough where it will actually succeed and hit the flag at certain points, right? So you see these spikes here. But the issue is that it's not learning enough, right? So it's not changing the weights enough such that it will start doing that consistently. In fact, the only way to do that is if you get really lucky and it hits the flag multiple iterations, and then it starts to, move the weights more towards where you want it to be, and then it'll start hitting us more consistently. But again, that's very, very unlikely. And so with PPO algorithms, with these policy gradient, what we call sparse reward tasks, it's not going to perform very well.
What sort of reward did you give? Like, could you do some reward where it's just, rather than whether or not it succeeds reaching the flag, but let's say distance from the flag?
Yeah, so that's something you can do. For this particular environment, it's already predefined, but the way they calculate the reward, I actually put it down here, is it's the, let's see, it has a sparse reward system. Sparse just means that you either get a big one or you don't get anything. And typically you want dense reward where it's slowly, you're getting more and more as you reach the place that you want. And so the reward is 100 minus the scalar times the action squared. And the action is just like, okay, 1 means go forward, 2 means go forward a little bit more than you would. -1 would be like go backwards, something like that. And the square just makes it positive. But otherwise, I believe what happens is if it just tries to go forward, it gets a pretty big penalty.
Gotcha.
And you notice here, it's like, okay, well, the bigger the action, the more it's going to subtract from 100, which is the smaller our reward's going to be. Which means that whatever you do, you want to try to minimize the amount of action you're taking. And so the local maxima that this agent learns is that, well, I'm actually better off just not doing anything. Just not moving at all than trying to move and then suffering a big penalty. So the sparsity, what makes this task so difficult is that you only get a huge reward if you touch the flag, but in order to do that, you need to incur a bunch of penalty to begin with. And that's just something that PPO doesn't do very well with.
Yeah, no, that makes sense.
Yeah.
Okay, thank you.
I had another question about the actually the mountain card whole thing. Yeah. So assume that you were able to define some reward system that was more dense. Then do you feel like neural architectures that have some sort of notion of memory, for example, a neural Turing machine, would be advantageous here?
Definitely.
Because then it would sort of be able to remember that my previous actions led to consistently higher and higher rewards, and hopefully would eventually reach the goal.
Absolutely, yeah. I think so. Yeah, this just happened to be a multi-layer perceptron. In fact, both of these graphs were generated using a multi-layer perceptron, but you can certainly swap out different networks, and they will probably perform better. In your case, neural Turing machine, you can use an LSTM as well. It'll sort of remember what it did previously, right? So then it'll sort of associates actions more to time. And in this case, yeah, I'm sure I haven't tried it myself, but I could see how that might help it out.
So in that case, if you did implement it, would PPO just like work out of the box, or would you have to make some modifications?
In this environment, you might want to make some modifications, because this environment that I use, like this task right here, this is out of the box. There's not many ways to change that, I think. You're gonna have to maybe create some wrappers if you want to really change like the sort of data you're collecting. Because obviously if you want to use a neural Turing machine, you might want to change whatever observations you're getting and feeding into it, right? So yeah, I think you would have to change more than just the architecture or the network. But PPO is really just the update rule. So that it would work out similarly, I would say. Yeah. Again, those are always places you can experiment with.
Okay, thanks.
Mm-hmm. And then a question from David: would the system do better if the value was more shallow? Yeah, probably. I mean, it feels like if it only went up here, I think this one, the optimally, it would come up here and then it would come back here, swing back here, and then it would get enough momentum to hit the top. And if it was a little bit more shallow, assuming it still can't just reach the top by going forward, it would still have to perform that sequence of actions. So yeah, I think it would hit the flag more often, but ultimately you're still running into the same issue that you need to perform the same sequence of actions in order to get there. It's just that here, if you made it more shallow, you're more likely to hit it because you don't need as much momentum. Yeah. Great questions, by the way. And if you guys ever get the chance, take CSC 150B. I think the next time my professor is teaching it is going to be next fall. So you might have to wait about a year, but it's a really cool class. And I don't think it's very heavy in terms of workload.
I had another question that was less related to PPO, but you mentioned at the start that you were working in Sean Gao's lab. Is that correct?
Yes, I am.
Could you talk about like what it's like to work in his lab?
So Sean's a little bit interesting because he actually doesn't have a lab. He does more one-on-ones with students, with his research people. So I'm currently working on a one-on-one project with him, and he does one-on-ones with his other students as well. But it's pretty chill, I'd say. You work on it when you have time, and the progress is really just up to you. Sean obviously is there to guide you, but ultimately you're the one in charge of your project. And that's a little bit of a different dynamic compared to other professors you do research under, because a lot of professors, they have a lab, they have their own PhD students, and everyone's sort of working together on one thing. And the thing about that is when it comes to assigning credit. And when you're writing research papers, there's a lot of people to assign to. And so you might not always get the credit that you want. The thing with Sean is that whatever paper you write, you're pretty much going to be the first author because you're the owner of that project. And it's nice to sort of have that feeling of ownership. I guess one of the downsides is you're obviously not working as much in a team. And so progress can be slower than if you had a whole team of PhD students to work on this thing. But it does massively help with your own learning curve, right? Because you have to be the one to basically do everything. And that means you're the one learning everything and getting the most out of it. Let's see. Can the system ever get in a loop where epsilon sub I, comma, oh, I think you mean epsilon sub I. System ever get in a loop where epsilon sub I, do you mean where you perform an iteration and there's no change? Can you elaborate? I think you're referring to where the iterations will take a path that gets to state. Oh, so it's like, okay, well, it just sort of loops back between two states. Is that what you're talking about? It's like what you sent. We're just sort of in a loop forever and ever. Yeah, I mean, that's something similar to, definitely, yeah. We actually just looked at it too. This mountain car, it just sort of swings back and forth like this forever and ever. The only way to sort of get out of this is during training, you have to set a quote unquote epsilon, which will tell you the percent of the time that you want to take a random action, right? So the actions that it takes is based on two factors. Number one is the policy, which will map the states to actions, and the randomness that you add to it, where it'll say, okay, 20% of the time, for example, I'm going to just pick a random action. And that's supposed to be its way of like finding better paths than just what it's currently at. But again, with these sort of systems, like for example, this task right here, having that randomness factor is usually not good enough when it comes to having a sequence of actions that'll take you from this point all the way up here, right? In order to get from here to here, you need to do this double swing thing. And the randomness usually just doesn't cut it. And that's why a lot of it's just luck. Mm-hmm.
Oh, else I found the thing that I was talking about with search. I completely misunderstood it. It's something different. It's when like you have a multi-agent game, and so one agent kind of everyone but one agent fixes their policy, and that one agent kind of explores, does online updating of their actions.
Oh,
yeah.
Thanks for bringing up multi-agent, by the way. Yeah, one thing, PPO is a single agent algorithm, which means that it's only guaranteed this sort of
protection, I guess, security.
Yeah, it's guaranteed this sort of that it works in a single agent environment, which is it follows the standard Markov decision process of you have one agent in one environment and they're just interacting with each other. The moment you introduce multiple agents, all of them, which, you know, let's say we have multiple agents, each with their own PPO and they're all learning, you're not guaranteed that you're going to get convergence. You're not guaranteed convergence. And that's something that we call the Nash equilibrium, I believe. But if you, I'm sorry.
I understand. The dynamics in those games are way more complicated. they get messy. But this still works for like partially observable Markov decision processes, or is it just for MDB? Okay.
Yeah, pretty much. And that's something I'm actually working on, is seeing how these single agent algorithms work in a multi-agent setting. Yeah, so it's an active field of research going on right now.
Okay.
Typically with multi-agent settings, you'll have different algorithms. And Jason, if you remember in 150B, we learned minimax, right? Constructing the minimax tree for 2048.
Yep.
That's a multi-agent algorithm where we have two players. You have player, was it white and black, or was it? It was computer and human, right? Those were the two players. And the go is like, okay, the computer wants to minimize the human's score and the human wants to maximize his own score. So then they sort of, when they're building the game tree, they pick the path that sort of suits their own decisions. And that's the multi-agent algorithm, is when you have both of them, you're taking account all the agents in one algorithm. Slightly different, very big difference between that and just multiple single agent algorithms in one setting.
Yeah, I don't believe the minimax stuff extends theoretically, at least, to like many agents. So maybe even, yeah, like maybe in zero-sum games to some degree you do have like a minimax optimization problem, but I don't think that like I'm not
Minimax
sure.
is
Minimax.
It's usually for two agents.
Two player, yeah. I don't think it extends to multiple.
Well, you can always you can add more actually. It's just like let's say you have agents that work in sequence, right? Let's say like you have three players and you do counterclockwise turns, right? You can still construct a sort of minimax for that, I believe. But if you have multiple agents and they're all, given a time step, they all do their own thing, minimax probably wouldn't do very well. Yeah. And another bad thing about minimax is it assumes discrete observation spaces and action spaces, right? Where it's like, okay, well, we're building this game tree. It's only as good as, how big we can make it, right? Now, that's only any good if our action space is discrete. We can either go left or we can go right. We can go up or we can go down. If it's like you have to pick, your action is pick any number between 0 and 1, any sort of decimal, right? Then suddenly you can't use these tabular methods. You can't build a tree off that.
Yes, definitely.
Yeah. So that's where policy gradient is really useful, is it allows you to work with these continuous spaces.
Yeah. That makes sense. Thank you.
Yeah. And any other questions you guys might have? I know we're out of time here. Feel free to reach out to me. I'll put my email in here.
Oh, thank you.
Happy to always chat about anything and everything. So yeah, hope you guys enjoyed the little Prezi.
Yes, thank you. Thank you very much. This was interesting.
All right. So I think we're going to end it off here. So again, Edward, thank you so much for inviting me. And yeah, hope you guys have a great day.
Thanks, you too.
Great. Thanks. Have a good day.
Bye-bye.